we can get started then. So sorry about the minor technical difficulties. Welcome everyone to the One World Combinatorics Onwards seminar. Our speaker today is Pranjal Jain from the Indian Institute of Science, Education and Research in Pune, India. And he is going to speak to us about partial sums of binary subword counting sequences.
Yeah, so thank you. So just a minute. Yeah. So a bit about me. I'm a grad student from India and I just completed a dual bachelor's and master's degree from Mysore, Pune. And I'll be joining UBC in the coming fall for my PhD with Alejandro Adam. And my research primarily lies in algebraic topology, and the work that I'll be presenting today was done as part of a summer project in 23. So let's get to it. And a few acknowledgements. So first of all, this work was done jointly with Shuoli, and it was done at UCAM in Montreal. And I would really like to thank them and particularly the Larsen group for their hospitality while I was staying there. And I would also like to thank MyTax who funded the whole thing and who also matched me with Shuo and UCAM as a whole. So without them, this wouldn't have happened. So now coming to the math. So let's start with W being a finite word over the binary alphabet. And for a non-negative integer n, I'll let SWN be the number of occurrences of W as a scattered subword in the binary expansion of n. So we'll see a few examples. And EWN will be the number of occurrences as a consecutive subword. So in the case when n is equal to 26, this is the binary expansion. So as a consecutive subword, it appears only twice. You have 1 0 here and 1 0 here. And can you see my cursor?
Yes.
Okay, the cursor is visible. That's good. So you have 1 0 in two places as consecutive subwords, but as a scattered subword, it appears many more times. So obviously these two consecutive occurrences are there, but the first one and the last 0 is also a scattered occurrence of 1 0. So that is also counted in S sub W of n. And I'll call this sequence where I just raise this SWN to the power -1 as a subword counting sequence. So it just keeps track of the parity of SWN, and likewise for EWN. And today's talk will focus on exploring when a given word W satisfies this condition. So basically, I'm saying that up to a certain capital N bound, the number of times that SWN is odd should be roughly the same as the number of times that it is even. And formally, I mean that it is like the error is O of n to the 1 minus epsilon. So in literature, similar questions have been explored for factor counting sequences since the 80s. But for subword counting sequences, there has been very little work. So of course, the work of Narad Rampasad and Jean-Paul Alouche is there in the area of subwords, but this particular question has not been explored much. So to get started, let's look at a recurrence relation for scattered subword counting. So the idea is that when you add a 0 to the end of your word and you double your n, then that changes the number of times W0 appears in a predictable manner. So of course, doubling n just puts a 0 at the end of its binary expansion. And so that means that if you want to count how many times W0 appears in 2n, that's the same as first counting how many times it appears in n, and then counting how many times W appears in n, and then just taking that 0 at the end into account. So that's where the first one comes from. And the second one is just saying that if you add a 1 at the end of your binary expansion, then that doesn't change the number of occurrences if your word ends with 0. So likewise, if you flip all the bits, then you get this recurrence relation. So now if I double n and add a 1 at the end of W, then nothing changes. And if I add a 1 here and add a 1 here, then I get a sum of two things. So some of these recurrences fail for n equal to 0. Of course, how many times 0 appears as a subword of the binary expansion of 0? Well, 1. But this recurrence would predict that it appears, and the number of times that 0, 0 appears in the binary expansion of 0 should be 0, because like the binary expansion of 0 just has 1, 0, right? But this thing would predict that it has one occurrence, which we don't want. So sometimes this fails for n equal to 0, and this will cause some minor technicalities later on. But for the most part, it won't matter too much. And you can just condense these recurrences into one nice equation this way. So if my word ends with a, this should have been 2n plus a over here. No, sorry, this is fine. Okay. So if my word ends with a, and the binary expansion of n ends with a, then I get a sum of two things. But if they end with two different things, like here, then just get one term. And of course, for subword counting sequences, which was -1 to the power SWN, you get a product over here. So the sum becomes a product, and here you just get one term. And the analogous recurrence for factor counting sequences doesn't involve a product of like multiple things like we get over here. So that is one of the major differences between the stuff for subwords and the stuff for factors. And now let's look at two examples of studying the growth rate of this sum. So let's look at the word 0, 1. So in this case, I can look at S2n plus 1. And the reason I'm going for 2n plus 1 and not 2n is so that the indices in both of these sums can be taken to be n. So this is taking account of all the odd terms, and this is taking account of all the even terms. And now since we have a recurrence relation, I just convert this thing into this, because 0, 1 ends with 1, and we are doubling n, we are not adding 1. And over here, 0, 1 ends with 1, and 2n plus 1 also ends with 1. So you get a sum of two things. And this 2 that you get in front can mostly be ignored. So it's just coming from the fact that here my sums are starting with 0, whereas here they are starting with 1. And that goes back to the fact that the recurrences don't work for n equal to 0. But it's not too big a deal. And now this sum that we have is just Sn itself, right? So there seems to be some nice recurrence falling out of this, but we are not quite there yet, because you also have this sum which involves a term with which like we haven't thought of so far. So you have a sum of two subword counting things. So no worries, let's just give it a name. Let's call it Tn. And now what you can do is use the same recurrence for Tn. So in the exponent, in the terms for Tn, this is what we had. We had a sum of two SWNs. So you just apply the recurrence to both of them. So now this thing ends with a 1. So when you take 2n, you just get back the same thing with n. But this ends with a 0. So when you have 2n, like the number of occurrences of 0 and 2n is 1 plus the number of occurrences of 0 and n. So that is where this plus 1 comes from. And then for this one, similarly, 0, 1 ends with 1, and 2n plus 1 ends with 1. So you get a sum of two things. Here, you just get the thing itself, and those two cancel out because we are working mod 2, right? So in the end, we are going to raise -1 to the power of all of this. So we only care about things mod 2. And so this is what you get. And this plus 1, so now you do the similar process that we did over here for S2n plus 1 to T2n plus 1. And this -2 again occurs because of some minor technicalities. And now you get a copy of Sn and minus a copy of Tn. And the reason that minus is coming is because of this plus 1. So when you raise -1 to the power of all of this, that plus 1 becomes a negative sign at the front. So you get these two recurrence relations, 1 and 2. And these will now give us all that we need. So if I add these two, then I get S2n plus 1 plus T2n plus 1 is equal to 2Sn. And now I can use the recurrence on this itself, right? So I get 4n plus 3, 2n plus 1 times 2 plus 1. And again, this minus 2 is because of some technicalities. And from here now, basically, what we are saying is that when you quadruple n, you only double Sn, right? So with a bit of analysis, you can easily see that Sn must be O of root n. And one of the things to keep in mind is that Sn plus 1, like the difference between Sn and Sn plus 1 is of absolute value exactly 1, right? So these Sns don't suddenly jump when you change n a little bit. They always change by 1, 1, 1. So that is why like this rough argument does go into a formal proof of why this is O of root n. And hence 0, 1 has property P, which we define to be that the sum of the subword counting sequences is O of n to the 1 minus epsilon. So in this case, we are taking epsilon equal to half. Now, similarly, you could take the difference of two of these two. And so you get S2n plus 1 minus T2n plus 1 on the left and 2Tn on the right. And once again, you use the recurrence on the left like we did over here. And in the exact same manner, you end up proving that Tn is also O of root n. So we didn't actually set out to prove this about Tn. We hadn't even thought about Tn, but we just got that result for free. So this is a theme that will pop up once again. But we proved, like in particular, we proved that 0, 1 has property P, which was the main result. Now, the big picture is that we had to use this recurrence relation for SWN twice. The first application was on Sn, and from that popped out a new summation Tn, and then we applied it on Tn once again. And both of these applications were necessary for getting the final result. We couldn't have gotten it without like by just doing one of the two. Now, yeah, the application on Tn did not produce any new summations, right? Tn was like we were able to write Tn just in terms of the previous summations that we already knew, Sn and Tn. So that's why we didn't have to apply the recurrence once again. And so these two equations gave us everything we needed. So this example contains most of the ideas, such as using that SWN recurrence and also the mechanism by which we get new summations, and we have to take those into account as well. But this new example, like a slightly bigger example of 0, 1, 1, will really capture the essence of the arguments and like drive home the point. So once again, we use the SWN recurrence on this summation, and we get 4 equations now. So these equations are in terms of all of these summations. So you don't have to remember precisely like the expression of each one, but the big picture is that you just get a sum of a bunch of SWNs in the exponent, right? That's really all that's happening. And one more thing to keep in mind is that all the W's which appear in these SWN expressions are prefixes of 0, 1, 1, right? So here you have 0, 1, 1 itself. Here you have 0, 1, 1 and 0, 1, which is a prefix. Here you have 0, 1, 1 and 0. Again, 0 is a prefix. And here you have all 3 prefixes. So it's always a sum of prefix terms that appears. And you get a bunch of linear equations in these 4 things when you change n to 2n plus 1. And of course, best way to capture this would be as a matrix. So you put these 4 guys in a vector form, and you look at what matrix you must apply to this vector to get the vector at 2n plus 1. So you just convert these linear equations into a matrix. So that is how we get this. Just to calibrate a little bit, when you multiply m to vn, the first row times this column will give you Sn plus Tn, and that should be S2n plus 1, and that is exactly what we have here. Here you have Tn plus Un, that should give you T2n plus 1, and that is exactly what we have here with a bit of a constant, which is taken into account over here. So basically, it works. So this is the matrix, right? And this matrix captures the essence of the problem we are working on. So this equation is what will play the main role in the story. So now, how can we? So the original goal was to bound S2n plus Sn, right? We wanted to show that Sn is O of n to the 1 minus epsilon. So it suffices to bound the norm of Vn because Sn is one of the components of Vn. So how do we use this equation to bound the norm of Vn? Uh, so let's say the binary expansion of n was this. So you have AIs, which are the digits. Then you have this relation, which is essentially the definition of what we mean by binary expansion. And I'll let xk be v sub n by 2 to the k, and I'll let delta k be this difference. And now observe that the norm of delta k is always at most 2. The reason is that xk, uh, sorry, yeah. So this m sub, this product, m xk plus 1 plus c, uh, will be v sub twice this thing plus 1, right? And ak is either 0 or 1. So the difference between uh, 2 times this thing plus 1 and n by 2 to the k is at most 1. So that is why, and like all of these SNs, TNs, they when you add 1 to n, these things change by at most 1. So that's essentially why delta k is always fairly small. And now I can just start using this recurrence over and over. So Vn is x0, and that is by this recurrence, it is this thing, and like the definition of delta. And then now what I do is I apply the same recurrence on x1. So I get m times mx2 plus c plus delta 1. So by regrouping terms, this is what I get. Then I apply it again. This is what I get. And you can see it's sort of a geometric series type of thing. So now if all the eigenvalues of M had an absolute value of at most 2, then we would see from this recurrence that the norm of Vn at most, like the norm of x0 is roughly twice the norm of x1. The norm of x2 is so the norm of x1 is roughly twice the norm of x2, and so on. So you get a doubling at every step. So that is why you end up with this. So in particular, if we show that all the eigenvalues of M have absolute value at most 2, then 0, 1, 1 would have property P. So to show that all the eigenvalues of M are smaller than 2 in magnitude, we don't actually need to find the eigenvalues explicitly. We can just we can do a little bit of algebraic manipulation. So we can write this M as a sum of two signed permutation matrices, by which I mean that they are permutation matrices and the ones can also be minus ones. So you have plus minus ones as the non-zero entries. And you have this signed permutation matrix, which has only non-zero entries on the diagonal, and this one, which is the permutation matrix corresponding to a cyclic permutation. So now both of these are permutation matrices, so they preserve the norm. And so if I look at AX plus BX for any vector X, then both of those terms, AX and BX, will have the same norm as X. So if M had an eigenvector with eigenvalue, okay, maybe I'm getting a bit ahead of myself. I'll just go with this. So if we had the norm of any x0 being at least twice the norm of x0, then that would imply that these two norms are the same by the triangle inequality, in particular the equality case of the triangle inequality. So now if x0 was an eigenvector with an eigenvalue lambda, then that would mean that both of these guys have an eigenvalue of lambda by 2. And in fact, the norm of that eigenvalue should also be exactly 2, right? Because it can't be greater than 2 because that would make the norm greater than 2, greater than 2 norm x3. And this is not possible. The reason being that any eigenvector of B must have non-zero entries, like all entries non-zero, right? Because it's a cyclic permutation. So it will just rearrange your entries in a transitive manner. So you can send every entry to every other entry. So if even one entry is non-zero, it forces all the entries to be non-zero. But then if all entries of your eigenvector are non-zero, then it can't be an eigenvector of A because A is negating certain entries, right? So any eigenvector will have to have zero entries in at least like either the first two places or the last two places. So A and B can't share any eigenvectors, but we already said that if M had an eigenvalue of at least two, of absolute value at least two, then A and B would have to share an eigenvector. So that is how we prove now uh, that 0, 1, 1 has property P. So to recap, Vn was this thing, and we found out that it satisfies this recurrence relation. And all eigenvalues of M are at most 2 in absolute value. And hence, we get that Vn is O of n to the 1 minus epsilon. So in particular, Sn is that, and 0, 1, 1 has property P. And as a result of showing that the norm of Vn is growing slowly, we also end up showing that Tn, Un, and Vn are growing slowly because they are the entries of Vn. And we get this for free, even though we never set out to prove this in the first place. And just a side remark, in this case, we can find the eigenvalues of M explicitly fairly easily, and they turn out to be 0, 0, and plus minus root 2. So in this case, again, epsilon equal to half works. And here, instead of O of n to the 1 minus epsilon, you can have O of root n, just like in the 0, 1 case. Now, the general framework in which we prove our results. So once again, W is a word on 0, 1, and I'll give its length a name L, and I'll assume that the length is always at least 2. So for any word with the same length as W, uh, I will define this function from natural numbers to the two binary bits, which takes n to this sum of SWNs over some of the prefixes of W. So I think it's best if I let you read this instead of me talking over it. So uh, the idea is that everywhere that UI has a 1, you take the prefix of W up to that point in the summation. And if you recall, the previous in the previous two examples, 0, 1 and 0, 1, 1, the exponents of -1 always had this form. They were S sub prefix of n, and then a sum of a bunch of these terms. So you can see where this is coming from. And during the current presentation, I will call these subword counters, even though this is not the name we give in the paper. And here's a concrete example. So if I have ABCD as my word, where all of these ABCDs are zeros and ones, then and U is 0, 1, 0, 1. Then since I have a 1 in the second place, I take the subword, so the prefix of this up to the second place, which is AB. So that is one term. And it has a 1 in the fourth place. So again, ABCD, which is the prefix up to the fourth place, becomes a term. So this is the general idea. Now for any bit 0 or any bit A, the recurrence, if I apply the recurrence for SWN to these subword counters, then you would expect something like this to hold. And the reason is this is precisely what we were doing in the previous examples, right? We saw that whenever you apply the recurrence to any SWN, you end up breaking that into a sum of bunch of terms, and that sum will be captured by some choice of U over here. So SA or W of U. So we'll see some examples. So in this case, where W is 0, 1, U is also 0, 1. If I take this of 2n plus 1, so just to keep track. This thing will just be S sub 01 of 2n plus 1, right? And 01 ends with a 1. So when you apply the recurrence, uh, you end up with a sum of two things. And the sum of two things is captured by the fact that you have a 1 in two places over here. And here, since I'm doubling n, I have a 0 at the end of 2n. That doesn't change anything. So I end up with the same 1 1 back over here. And this plus 0 and plus 1 are coming from the fact that when I double n, I increase the number of occurrences of 0 by 1. So I'll just give you a minute to absorb this and wait, like stop for some questions if there are any. Okay, so it seems this part is clear and this part is quite important. So this S sub A of W is now a function from the set of all words of length n or length L back to the same thing, because that is essentially what is happening over here, right? So if I fix only a W and I don't fix a U, then I basically just get a function. And this I'll call an A split function for reasons that will soon be clear. And this extra bit that you end up with the end will be called a carry function. An A carry function. A is this thing which is in the subscript. So here's how to calculate these guys. So you have some choice of W, some choice of U. What you do is that each time a 1 appears under an A, so in this case, A is equal to 1. So you look at all the places where 1 appears in W and you check whether there is a 1 below that in U or not. So if there is a 1 in U, then that sort of splits to the left and adds 1 to the term in the left. So here you can see that this one goes down unchanged and it adds a 1 to the thing on its left, right? And you can go think back to the recurrence for SWN that we had and see that this makes perfect sense. And similarly, you have something happening over here. So you have a over here, A equal to 1. And below that also we have a 1. So that splits to the left, adds 1 to the thing on the left. So now 1 plus 1 becomes 0 mod 2. And this one also splits off and puts a 1 in the left. So you get a 1 over here. So this is how you calculate S sub A of W of U. And for A equal to 0, again, it's the same thing. You check where all you have a 0 in W and you check whether there is a 1 below that. So in this case, there is a 1 here. So that splits off to the left and adds 1. So this one becomes a 0. But below this 0, we don't have any 1. So nothing happens there. So this is the general idea. And TAW of U captures the split which spills over from the leftmost digit of U. So in this above example, if I look at T0, that is going to be 0 because there is no 0 in the first place of W, right? So there is no splitting happening over here. Whereas T1 is 1 because if there was something to the left further here, then this 1 would have split off and added 1 over there, right? So that spillover, which is not captured by S, is captured by T. And this is, again, you can see why that appears in this formula going back to the recurrence for SW. We saw that S0 of 2n was S0 of n plus 1, right? So that's basically the phenomenon that's being captured here. So now I hope this recurrence makes more sense. And just for completion, I will mention that there is a fairly simple logical formula that you can give over here. And by logical, I mean that here this O plus is basically an XOR. This is a logical operator of AND. This bar denotes negation. So you don't have to keep this formula in mind or anything. I just put it here to show that this can be captured in that way. Now, some basic properties of these splits and carries. The first is that if I take a sum of two u's, then that sum breaks up into a sum of two s's, or two splits. And one way to say that is that these split functions are group homomorphisms, right? Where my groups are basically the groups of words of like the group of words of length L. That's a group under XOR. Um, and the reason for this is quite clear over here, right? If I add two things, then the splits that like the split overs that happen to the left also add. So that's why the whole thing breaks up into a sum. And the same thing happens for T again, because T is also coming about because of these splits, the spillover that happens. Um, if W prime is a suffix of W and U prime is a suffix of U with the same length, then this split is a suffix of this one. Again, that is fairly obvious because um, whatever splits are happening over here towards the right are not affected by anything. Yeah, okay. Can you see the screen now?
Yeah, everything's
Okay.
back.
Yeah. So suffixes are preserved by splits because whatever is happening to the right is not affected by what's happening to the left. And this is a bijection. So this is again not too hard to prove because you can sort of see that from this logical expression that you can reverse things, but I'm not going to details of the proof. And just a little definition, if I take a word, a binary word of length r, then I'll define S sub h of W of u to just be the composition of all of these guys. So each of these, recall, is a function from 0, 1 to the L to 0, 1 to the L. So in fact, it's a permutation because you have a bijection over here. So you have, so this is just a composition of all of those permutations. And yeah, so in light of this last point, that this is a bijection, the set of all these split functions for a given word, W, forms a group. Because, so you might say, okay, where are the inverses? Well, that's just coming from the fact that this is a finite set, right? So if I just show that it is closed under multiplication and it has an identity, which of course is there in this case, then it is a group. I don't need to show inverses separately. And since I have a group, I can ask what it acts on. Of course, it acts on 0, 1 to the L by definition. So let OW of U be the orbit of any given word U under the action of this group. And special emphasis will be placed on this word, which has all zeros except in the last place. So I'll define this orbit to just be O sub W in that case. I'll omit this 0 to the L minus 1. And now going back, like connecting all of these definitions to the previous examples that we looked at. So this orbit of 0, 1 is just 0, 1 itself and 1, 1. And you can see that because if I apply S sub 1 to this U, then that's gives you a split to the left and you end up with this word. Whereas if you apply a zero split, then nothing changes because you don't have any ones appearing under the zero. And one thing to notice is that whatever elements you have in this orbit are also the things that go down here in the expressions for these SNs and TNs that we had. And likewise for 0, 1, 1, you have more things to keep track of, but the same thing still holds, that the elements of this orbit are precisely what you get in the exponents of all of these things. And there is, importantly, there are no extras in the orbits and there are no extras in these summations either. There is a perfect 1-1 correspondence, and we'll see that this is a pattern which holds in general. So Now I'll come to the matrix vector formulation of the whole situation. So let so there are lots of letters here and I can't really read it. So I'll just say the first letter. I'll just say V. So let V of n be this orbit size dimensional column vector, and it's very natural to index its entries by the orbit itself. Its entry in the u prime position, where of course u prime is a word of length L, is this entry, and you can see that that is basically what's happening here. Recall that we had put all of these guys in a vector, right? So basically what you get for an arbitrary W is the perfect analog of what we had for 0, 1 and 0, 1, 1. And for the matrix, I'll define M sub A to be the matrix again of size orbit cross orbit, and I'll index the entries using the orbit itself. Its u prime comma double prime entry will be this. So you take the spillover and raise it to the raise -1 to that power, and that appears in any given entry if and only if uh, applying an a split to the first coordinate gives you the second coordinate, right? So a split on the first coordinate gives you the second coordinate, and all other things are 0. And I'll define M to be the sum of these two things. And recall that we had two signed permutation matrices which were giving us the whole matrix in the previous example. That's exactly what's happening over here. So, of course, and by the way things are set up, this is precisely what we want, that V of 2n plus a is M times V of n. Um, And now I'll define capital V of capital N to be the sum of all of these things. So if you think about it for a minute, what will the entries of V look like? They will just be sums of these sort of things. And what are these sort of things? They are exactly what appear in the terms of these. So the capital V of capital N that I just defined is exactly the vector that we had in the previous example. So now the recurrence for small v gives you this thing for capital V. So capital V of 2n plus 1 is m times capital V some plus some constant c, which we don't need to worry about. And once again, uh, if we are able to show that the eigenvalues of this matrix M have absolute value at most 2, then the norm of this thing will be bounded by O of n to the 1 minus epsilon for some epsilon. And that will say that all of these sorts of summations are grow slowly. They are O of n to the 1 minus epsilon. And when that happens, uh, when the norm of capital V is growing slowly, we say that this pair W comma U has property Q. And I just want to point out a uh, quick subtlety over here, that I am not saying that the pair has property Q if M has all eigenvalues of absolute value smaller than 2. This is only a sufficient condition. The definition of having property Q is just that this equation right here has to be satisfied. So it could be in principle that this equation is satisfied without the eigenvalues being smaller than 2. So it is the eigenvalue thing is just a sufficient condition. And if W comma 0 to the L minus 1, 1 has property Q, then in particular W has property P, because one of the entries of capital V will precisely be your partial sums of the subword counting sequence. So again, this is only a sufficient condition. It's not a necessary condition. So in principle, you could have W satisfying property P, but this pair doesn't satisfy property Q. I haven't found any examples like that, but it could happen. So previously, like in the current setup, you can summarize what we did for 0, 1 and 0, 1, 1 by saying that we showed that both of these pairs have property Q and used the fact that it's a sufficient condition to conclude that both of these words have property P. So we have already been through all of this just in a special case. Yeah, and just to further drive home the analogy, your capital V for the 0, 1 case was exactly Sn, the vector with Sn and Tn, although we didn't think of it as a vector at the time. And the two equations we had for S2n plus 1 and T2n plus 1 can be captured by this matrix. Again, we didn't think of it in the matrix vector form, but it can be done. And for the 0, 1, 1 case, sorry, I think I messed up. This thing should have been 0, 1, 1, and this thing should have been 0, 0, 1. Yeah, I've written it correctly for this one. So in this case, again, your vector has all of these summations as entries. And this matrix is precisely the same as what we called M previously. And the two permutation matrices are precisely M0 and M1. So everything that we did previously was exactly the same as this. So now, of course, coming to some basic properties of M, it's a sum of two signed permutation matrices. This time it is by definition, even though while we were talking about the 0, 1, 1 example, that was sort of something which we noticed later on. And now if X is an eigenvector of M with eigenvalue of absolute value at least 2, then just like in the 0, 1, 1 case, the eigenvalue has norm exactly 2, it's not greater than 2. And also X is a common eigenvector of M0 and M1 with eigenvalue lambda by 2. This is because both of these are permutation matrices and they preserve the norm. So again, we use the triangle inequality. And all entries of X have to be non-zero. Again, this is something that we saw in the previous example, that one of the two permutations was a cyclic permutation. So that forced any eigenvector to have all entries non-zero. So in this case, it could happen that neither of these is a cyclic permutation, but you can still show that all entries of X are non-zero. And the overarching strategy in our work is to convert all of these linear algebraic statements into combinatorial ones and in terms of the words. And this will lead for some sufficient conditions for this pair WU to satisfy property Q. And hence, if you put U equal to 0 to the L minus 1, 1, then you get a sufficient condition for W to satisfy property P. Now for the results. So here's one. When let A be any digit, then the word which is just A repeated L times satisfies property P if and only if L is a power of 2. So one thing to note here is that so far everything I told you has only been sufficient conditions for when something can satisfy property P. But despite that, we were able to add some more tricks to our method to show that it to sort of demonstrate that we can sometimes also prove when something doesn't satisfy property P. So this is one of those examples. So for example, if L is 3, then property P is not satisfied. Now the next one. So this one was a 1-run word. So now the natural next step is a 2-run word. So it will look like a bunch of ones and then a bunch of zeros or vice versa. So all of these guys satisfy property P. And in general, you can also give a bunch of examples for when this thing appears in some pair which satisfies property Q, but I'll not go into that right now. So yeah, and of course this covers the 0, 1 and 0, 1, 1 cases from before. Now here is an example which only gives you a statement about property Q. It doesn't say anything about property P. So it's a sort of a bit complicated, but basically what is being said is that you have a bunch of, let's say ones. So let's say A is equal to 1. You have a bunch of ones, then you have an arbitrary word, then you have a 0, and then you have a bunch of ones again. So if you have that sort of a thing, then you get something satisfying property Q. And to really drive home the point, let's take K and J equal to 2 and A equal to 1. Then any word V which starts with 1, which is fairly surprising. So previously, what we were mostly caring about was -1 to the power, let's say, SV of n. But now, basically, what this result is saying is you can just add a small term in the end, and then everything is growing slowly. And there are like the conditions on this V are fairly weak. Like I'm just saying that it starts with 1 1, ends with 0 1. In the middle, you could have a million digits of which take any form. Right. So this is fairly surprising. And of course, you can increase K and J to get more things like this. And now, here's another example of property P. So in this case, the keyword which is appearing is this thing. So what we have is that you have a bunch of ones. Like again, I'll assume that A is equal to 1. You have a bunch of ones, and you have exactly a power of 2 number of them, and that power of 2 is also large. So it's large enough that you don't have a single run of these many ones in W itself. So it's a sufficiently large run of ones, and then you have a 0, and then you have an arbitrary word. So in such a case, property P is satisfied. Once again, you can get a more general statement about property Q. And a quick exercise for those who want to test whether they've understood these definitions properly is that just try to see why the second statement implies the first. So you'll have to untangle all of the definitions that we've gone through so far. And one quick example would be that this word satisfies property P. So some further directions for where this can go. So the first obvious limitation, as I said, was that techniques mostly don't uh, give you a way of showing that something does not satisfy property P or property Q. But of course, in one simple case, we were able to show that something doesn't satisfy property P. So hopefully, future work can use that as a jumping off point to show that or to get some necessary and sufficient conditions. And we also used property Q as a stepping stone for property P. So again, our overarching strategy was to show that something satisfies Q to show that it satisfies P. But we cannot show, like our methods don't allow for showing directly that something has property P. So it could happen in principle that you have something like this which does not satisfy Q, but W does satisfy P. And another hindrance was that we used the statement about eigenvalues of M as a sufficient condition. So it could happen in principle that M has some eigenvalue, absolute value too, but the pair of words WU still satisfies property Q, even though our methods don't allow for proving that. And there are some generalizations that can be done as well. So um, here what we are doing is, instead of looking at binary words, you look at base B words. So you look at how many times some given word W appears as a subword of the base B expansion of N, and then ask the same question, that if I take this summation, does it grow slowly? So our setup can be generalized to this case. And what will happen is that instead of just 0 splits and 1 splits, now you'll have a split for every base B digit. And again, all of these matrices will be permutation matrices. So you can use similar ideas over there, that something like if you show that all of those split matrices cannot have a common eigenvector, then you will be done. So we did not try to do this ourselves, because we just wanted to focus on the main ideas. And you can generalize even further by, now instead of saying that you're reducing things modulo 2 by raising things to the power -1. You raise things to the power of like a primitive root of identity. So if it's a dth root, then you are basically looking at things modulo d. And once again, you can ask whether this thing grows slowly. So these our setup can be generalized to this case as well. So instead of signed permutation matrices, you will have sort of permutation matrices with ones replaced by dth roots of unity. So it is fairly analogous, but of course that could add some challenges. And in the in the d equal to 2 case, which is what we studied so far, you can interpret this growing slowly statement to say that SWN is even and odd roughly equal number of times. So for d equal to 3, also that interpretation holds that SWN is roughly 0, 1, or 2 mod 3 the same number of times. But if you increase d, then this interpretation does not work. And that's it. I'll stop here. Thank you.
Great. Thank you very much. Does anyone have any questions? Hajime.
Thank you for nice talk. I have a question about the binary or original case. So
Okay.
we can
Can
consider
do you have a particular slide number in mind?
So my question is not in your in your original question, but my question is the ratio of the number of binary words of length n, which
Sorry, your voice is
satisfies
breaking.
So the number of binary words of length n, which is can you listen to me?
Yeah, now it's clear.
So the number of binary words of length n, which satisfies the property p. I'm interested in the ratio of
Okay.
it tends to 1 or 0 as n tends to infinity.
Yeah, that's an interesting question. So I haven't thought about this, but let me just quickly see if our existing results say anything about this. So I think we have something on property P over here. So you could probably get a lower bound on that ratio using this, right? I think it's fairly easy to see how that would come about. But yeah, I don't think our results will directly show you that, like give you the exact value of that ratio, because as I said, we don't have any ways of understanding when something does not satisfy property P except for those simple cases. But yeah, that's an interesting question to think about.
Thank you.
Jean-Paul.
Yeah, thank you. Thank you for the nice talk. I have a question which might be related to what was just said. You have the property P with exponent 1 minus epsilon. And my question is, do you have a characterization or at least a large bunch of a large family of sequences for which you can take this exponent equal to a half? 1/2.
No, so our methods don't allow for estimating epsilon, because if you look at what we did, where can I? Yeah, okay, this one. So we just use the fact that both of these guys are permutation matrices, and hence if something was an eigenvector, then it would have to be a common eigenvector, and we just studied when that does not happen. So when you cannot have an common eigenvector, so that does not say anything about uh, how large you can take the epsilon to be. But in the two
Right.
examples that we studied, since the matrices were small, we could find the eigenvalues explicitly.
Okay, thank you.
Are there any other questions?